Hello, my name's Tim Colson and I'm one of the Science of the Times podcast co-hosts. When I woke up this morning, I do what I often do is I kind of flick through the science news. There was an interesting story on the BBC that said that there was a race between American scientists and Japanese scientists to work out why the universe existed. I kind of thought that was a fascinating story, but it was, as many science stories are in the press, a little bit vague. So I thought I'd explain what's going on in a little bit more detail. So there are two teams, one in America and one in Japan, who are trying to work out tiny little differences between matter and antimatter. Now, most of the everything in the universe that you see, or nearly everything in the universe that you see, is made up of matter. But there's something called antimatter, which is similar to matter in many ways, except it has a different charge. So, for example, something called a proton has a positive charge, whilst an antiproton has a negative charge. And when matter and antimatter come together, they annihilate one another in a huge burst of energy. And theory says that when the universe formed, there should have been equal amounts of matter and antimatter, and therefore we'd have expected them all to explode in a big annihilation, a big bang of energy, and there wouldn't be anything in the universe. It would have disappeared. Yet for some reason, a little bit of matter survived. So that either means there was a little bit more matter than antimatter when the universe formed, but scientists don't think that's right. Or there's some subtle differences between matter and antimatter that gave matter the upper hand. And indeed, what these two scientific teams are trying to do, one in Japan and one in America, is to try and work out, using huge detectors, whether a particular type of particle, a neutrino, differs a little bit from an antineutrino in a way that can explain why matter won out in the very, very early universe. Neutrinos and antineutrinos are very tiny particles. They used to be thought to have no mass at all, so no weight in other words, but it turns out that they do weigh a very tiny amount. And when they travel from one location to another, they tend not to interact very much, and that's because they only interact via two forces, gravity and the weak nuclear force. They don't interact via the strong nuclear force or electromagnetism. And that means that they're produced, they're very common, huge numbers of them pass through the Earth every second without hitting anything. They pass through you without causing you any damage. But very occasionally a neutrino will interact with another particle, something like a proton or an electron, through the weak nuclear force, and that can be detected, but the detectors to detect that need to be enormous. Now, when neutrinos travel, they actually change a little bit, and this is kind of something the BBC said but didn't explain why. Now, there are actually three generations of matter, and nearly every matter, the matter you see in your everyday life is in the lowest generation, the lowest energy state. But there are two higher generations where most matter doesn't exist in that state for very long. When neutrinos travel, they might start out as sort of an electron neutrino, and then through quantum processes, they might flip to being more muon neutrino, or the third generation. So they kind of flip between these states, which is kind of quite unusual. And there's some evidence that, in fact, the rate that they oscillate, it's known as neutrino oscillation, that the rate between they oscillate between these states differs a little bit between neutrinos and antineutrinos. And what the scientists are hoping to find is to actually characterize whether that difference is real and whether that difference is sufficient to explain why matter won out over antimatter in the early universe. Now, the Japanese team is a little bit ahead. Their detectors, so their experimental setup, it should start running in the next couple of years, while it's going to be a few more years before the American team sets up. Now, both teams might be able to work out this difference. The Americans' team detector is a little bit different from the Japanese team, so the Americans are saying that even if the Japanese get there first, their experiment will still be valuable because it's going to tell them a load of information that the Japanese team can't detect. And I'm sure that's true. So anyway, exciting times, but we're not yet at any point to explain why there is something rather than nothing. But who knows, perhaps some hints about that might appear in the next few years. Let's hope so. Hope that little explainer was useful. Thank you.